I will.
Oh gosh, there's a TH. There's a TH and a PH.
I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to guide our steps today. Help us to glorify you what we do and to understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. So today, talking about conservation of angular momentum. All right. And so we're going to work on deriving this for really. I think it's a spam call every day. Uh-oh. Hello? I'm teaching. I'll call you back. All right, bye. Bye. It's Dr. Budarez. It seems appropriate. Let's see here. So, if it was any other professor, I wouldn't take the call, but you know. Okay, so suppose you got x, y, z coordinates, and let's suppose we have n masses, m1, m2, m3. You get the idea. So maybe I got m1 here, I've got m2 here, you know, m3 over here, and so forth and so on, right? All the way out to the nth mass. And of course, every one of these is at some position vector relative to the origin, r1, right, r2, r3. This one's at the nth position vector, rn, right? So what I'd like to show is that the angular momentum of this system satisfies a certain relation, all right? And so what we need to do is we need to think about, first of all, how do you calculate the angular momentum of these n masses? So I'll start with that. So first of all, the net angular momentum is going to be m1 r1 cross v1 plus m2 r2 cross v2 all the way on out to mn rn cross vn. And I'm probably going to get tired of writing that, so let's just write this is the sum I equals 1 to n of m sub I r sub I cross v sub I, where v is the velocity of the ith particle. V sub I is the velocity of the ith particle. All right. So in short, what I'm saying is that, you know, obviously this would be like the angular momentum of the first one. This is the angular momentum of the second mass. This is the angular momentum of the nth mass, right? So in short, the net angular momentum is the sum of the angular momentum, menta. Now, so if we think about this, we can write down, you know, Newton's second law for each mass, right? Like, what's the net force on each mass here? So what I write here is that the change in moment, and I guess I should probably, we could repackage this a little bit, right? We could say this is really what? This is, you know, let me just make a slight adjustment here. Sum I equals 1 to n of r sub I cross p sub I, where I is the, where here p sub I is equal to m times v sub I, right? It's the momentum of the ith particle here, all right? So, of course, we know Newton's second law applies to each mass, and so we can write down the following: dpi dt is equal to, let's say, F sub I, which, if we think about the net force on the ith particle, Well, there's two pieces to it, right? The net force on the ith particle consists of the part of the force which is from external to the system, right? So the external force on the ith particle, right? So perhaps we have the system and gravity's acting on it, right? Gravity is not coming from the system, it's coming from outside the system if we want to think about the system as an isolated one. But there's also all of the forces that are internal to the system, right? Like you could imagine that the masses are connected with little springs or something, and those springs are themselves massless, et cetera, et cetera. You know, there's all these internal forces, and so those I'm going to say the sum j not equal to I of f, let me stick with my notation here, Fij, all right? So, great. So notice that we can differentiate. We can calculate what is dLi dt. Let's do that. So here we go. dLi dt. This is ddt of the ith position across the ith momentum, all right? Which the product rule tells us is what? This is really dri dt cross pi, right? Plus r sub I cross dpi dt. So you guys tell me, why is that first term there 0? So like, why is this 0? Can you guys tell me? What is this? This is another way of writing this would be what? We're actually looking at the velocity of the ith particle, right? Cross product with the momentum of the ith particle times the velocity of the ith particle, right? So what we're looking at is the velocity of the ith particle across itself, but any vector across itself is what? It's 0, right? So this is 0. But this right here, right? That's the force, the net force on the ith particle. So we have, lo and behold here, r sub I across the net force on the ith particle. All right? But we know also that we can express that ith force. We can put that in here, right? And so this shows me that, in fact, dLi dt is going to be equal to r sub I cross the external force, the ith one, plus, and I can pull the summation outside of the cross product because the cross product is, you know, additive. The algebra of the cross product allows me to pull out the sum. So I have the sum j not equal to I of r sub I cross f sub ij, like that. So that is the change with respect to time of the ith angular momentum, all right? Now, if I want to find the net change in the whole angular momentum, I have to add those up, right? I have to take the sum of those. So what would dL dt be? dL dt would be the sum. Well, I'll do 2 steps here. So we're talking about ddt of the sum I equals 1 to n of L sub I vector, right? And because the derivative is linear, we can pull the summation outside of the derivative, like so. And then we've got dli dt like this. But we already know that dli dt is what? Right above here, right? We can take all this stuff right here, right? And that goes right there. And as such, I have the sum, I equals 1 to n, of r sub I across the external force on the ith particle, plus, I'll write this as a separate term, the sum over I, the sum over j not equal to I, all right, of r sub I cross f sub ij. All right. Now, so can you guys tell me what is this right here? What would you call this? What would you think this is? What is this? If I talk about the net external force on the ith particle, and I take the cross product of the position vector and the ith particle with that external force, what is that? That's a torque, right? That's the external torque on the ith particle. So this right here, we could call it torque external on the ith particle. All right? Now I'm going to get the projector out here in a second and show you why. But this right here, this works out to 0 as it happens. Because what happens is that the torque of the ith on the j and the torque of the jth on the I, they're equal and opposite, and they cancel. And as we add over all possible pairings, that all cancels out to 0. In other words, a system of n masses can't torque itself in total, right? The net torque, all these internal torques, they all cancel out. And what we have then in a summary here is simply dl dt is equal to the sum I equals 1 to n of r sub I across the external force on the ith particle, which again is the sum I equals 1 to n of the external torque on the ith particle, which of course we could just simply call, by definition, the net torque external. Of course, you could justifiably just say it's the net torque because the net internal torque works out to 0. So the net external and the net internal, the sum of them is the same, you know. And this right here, my friends, is, well, it's not exactly conservation of angular momentum, but it's almost that. Conservation of angular momentum is a corollary to this equation I just boxed. What is it? If the net torque, then dl dt equals to what? 0. What does that mean? That means that the angular momentum is conserved, right? If the net torque on a system is 0, the angular momentum is constant. Any questions? Again, I'll get the projector out to show you the part I skipped over in a bit. But before I do that, let me give you an example which is a little bit more, well, it's kind of a silly example, but it's an example we usually do. And so the example is this. Suppose you've got, like a record, all right? And suppose the record is spinning with an angular velocity omega naught, all right? And the record has mass m. Maybe it's not a record. Maybe it's a merry-go-round, all right? So you got a merry-go-round. It's spinning at angular velocity omega naught to start with, okay? And then somebody drops a dead cat covered in peanut butter, so it'll stick. All right, so it'll stick, yeah. And then, so they just drop it, and then it sticks. It gets a little, it's dropped from a great height, so it's a little smushed. Anyway, so they drop the cat that has mass m, and let us suppose it sticks here, center of mass at radius, let's say, little a, all right? And let us suppose that the radius of the merry-go-round is r. So the question is this: if you drop it vertically like this and it just sticks, what's the final angular velocity of the system after the cat covered in peanut butter sticks to the merry-go-round? I kill cats in this class, so if you don't like if you don't like human on cat violence, or just general any kind of harm coming to cats, don't take my class. It's part of my brand. Sorry, I have no merch yet. I'm working on it. What would you guys like to see in my merch? I'm curious. Are there any particular things you guys want me to do? Eventually I'm getting around to it, but. What's that? A blue shirt? I have been looking for somebody who sells like a blue button shirt through like one of the, there's about 10 different choices for like merch shops for like YouTube channels that are easy to set up through like, whatever, Shopify or whatever such thing. None of them have like a button shirt that's not, I mean, they've got these like, these ones for like hipsters or whatever. They're, Hawaiian, and they've got short sleeves, and they're like $70. That's not what I want. I want long sleeve. I want blue shirt. And if I could get an embroidery of Cook on the back, that would be perfect. That's what I'm looking for. I haven't found it yet, though. Anyway, so if you happen to know somebody with like a startup who's really itching to like work with somebody to sell some blue shirts, like I'm game. But I'll shut up. So in this system, there is no torque external to the system. The process of the cat falling on the record, that does not put a torque on the system externally. Like anything that's going on, it's cat on merry-go-round, right? Gravity is like this, up and down. It does not put a torque on the rotation like this. The rotation's like this, gravity's perpendicular, I mean, gravity's axial to that. You can't produce a torque in this sense with a vertical gravity, all right? So the torque the external torque is 0 for this problem, which means we can conserve angular momentum. We can say that the initial angular momentum is equal to the final angular momentum. The initial angular momentum is I omega naught. The final angular momentum is and here I is I'll call it I1, is I1 plus I cat omega f, right? Because angular momentum is I times omega. What is the angular moment of inertia? 1/2 what? M big R squared, because it's a disk, omega naught, is equal to parentheses 1/2 big M R squared plus, what's the moment of inertia for the cat? I didn't tell you the geometry of the cat, but let's assume that the cat's like a point mass, all right? Because if details aren't given, you can assume that the object's a point mass, all right? So what's the moment of inertia for a point mass, a distance a away from the rotation axis? What is it? Uh-oh. M what? Yeah, little m a squared. And there you go. So we can solve for omega f, and we get the final angular velocity is equal to 1/2 m big R squared omega naught divided by 1/2 big mr squared plus little ma squared. And there you go. So this is like a very common, I've asked this on many tests in some version or another. This is like my go-to angular momentum question. I don't know how you'd solve this without angular momentum, by the way. Right? Do you guys know anything like in terms of like real world applications that involves conservation of angular momentum, where you've got like spinning things, they're coming together? How about like a clutch in a car? It's kind of like this, right? You've got spinning discs, they come together. There's some kind of like, you could think about angular momentum and torque there. All right, let me get my handy dandy. I would talk more for you today if we actually had air conditioning in this place. I want to go home. I'm tired of being in this building today. I don't know about you, but like, am I the only one who's hot in here? I have been hot all day. I did it to you. You didn't notice until just I said it. Maybe it's not bad in here. Maybe it's just me. It's my imagination. All right. I will eventually find my notes. Give me a second here, guys. How many blue shirts do I have?
Is it just the same shirt every day, or multiple?
No one really knows. I never turn on the lights in my closet. I just go in there and grab something, so I'm not really sure myself, you know. Like,
It's like the scene from The Grinch, where he like puts on the pants. So you do your laundry every day then? So then you have to have at least 4 people.
all right. Did I ever prove to you guys that I'm Batman?
Huh?
Did I ever prove I'm Batman to you guys?
No.
I mean, I've never seen you and him in the same room, so.
Did you do it on the
It's true.
board?
Doing the what? I can't prove I'm Batman on the whiteboard. No, I actually need. Give me a second here. I'll load it up here. All right, let's see here. Make sure I got the right one. Oh man, that's not the one. Ah, here we go. This is the Wu-Tang name generator. For example, rather famously, Donald Glover. Childish Gambino. This is where that name comes from. There you go. You feel educated? Yeah, there you go. Check this out. As you can see, Thunderous Night. As you can see, Thunderous Night. Therefore, to a Wu-Tang name equivalence, I am Batman. What does that even mean? No one knows. Don't question the Wu-Tang name generator. Oh no, there's a finite list. And not all the names are Liberty approved. So actually, I don't know. What's Liberty approved is kind of a, you know. Are we allowed to dance now?
For 40 minutes, then you have to stop for 20.
40 minutes, then you have to stop for 20.
Wait, what?
Oh,
There's
dang.
some weird
Yeah,
rule
that
about it like
41.
that.
What, is there any kind of limits on like what kind of music we're talking about,
I
or
have no clue.
are we
There's
like?
some random time thing where it's like you can dance for so long that you have to stop, and you have to dance, and then you can dance again.
I'm like, is it just you, or can your friends also dance?
It's one at a time.
One at a time? Oh,
Not social dances.
all right. Let me see here. I will eventually. There we go. All right, let me find my laser. So I was just going through this derivation with you guys, and we got basically through it, except for this calculation right here. there's not really much going on here. What I'm doing is I'm taking the sum over j not equal to I, and I'm splitting it into two pieces. Either you've got I less than j, or you've got I greater than j. Them's your choices, right? We don't have I equals to j because I is not equal to j. So you have this and that, and then I change I and j to L and k because I can. I just relabel the sum. And then my next step here, you notice, is I have flippity-flopped the FLK to FKL. What's going on there is Newton's third law. Third law pair says that the force of the ith on the kth, the force of the kth on the lth is equal to minus the force of the lth on the kth, equal in opposite direction. That's a third law pair. So Newton's third law come into play right here. Beep up. And then I just traded L greater than K for K less than L because it's the same thing. So just relabeling. At this point, I'm like, hey, hold on a second. This is the same stupid thing. So I then relabeled this to I less than J. It's not quite the same thing because this is a J, whereas that's an I. So I got like that. And then I take the difference here and put it into one sum. So I've got Ri minus Rj cross Fij. But Newton's third law, there's more to it. It says that third law pairs come in a pair, and they're directed what? Along the line connecting the masses in equal and opposite directions. That's the third law pairing. So that means that Ri minus Rj is collinear. It's parallel, if you like. I should probably say parallel. It's collinear to Fij. But the cross product of collinear vectors is 0. And there it is. So like the conservation of angular momentum is very, very much tied into Newton's third law. And this, as you can see in this calculation. Anyway, obligatory. Is this on the test? Please ask me if it's on the test.
Is this on the test?
Now that you've asked, sure.
Dang it.
Do I want to grade this? No, obviously not. Come on. You can rest in the laziness of my grading. I don't want to grade that ever. But I would like you to know about it, which is why I'm spending class time on you. You should understand these things are derived from vector calculus. Now, so we've talked a little bit about this again. Let me just review again. If we have an axis, we have a radius, we've got motion along a circular arc. We can understand that, of course, by Newton's second law, mass times the tangential acceleration is equal to the tangential force. That is true, but we can, of course, also look at that in terms of torque. Namely that I alpha is equal to the torque applied, right? And so how do you calculate the torque specifically? You need to find the part of the force which is perpendicular to the radial arm, right? So if the picture looks like this, we did a cross product the other day, right? But sometimes we don't need a cross product. We just need two-dimensional plane geometry to figure out the part of the force which is perpendicular to the radial arm. So if that's the angle, we just need sine phi times f, right? That gives me the part of the force which is producing the twisting motion, right? So in this case, the torque would just be Rf sine phi. Here is a problem which is, I'll come back to this problem another day, guys. I'm not going to do this one today. We'll come back to this one. The one I'm just skipping past is it's the Atwood problem, but the pulley's massive. All right, so I want to take like maybe 15 minutes to work that out a different day. Since I've got the projector out, I'd rather talk about this one today. Suppose you have a cylinder of mass m and radius r, and you got a small mass like that, all right? And it's placed at an angle theta relative to the, as pictured here. And this mass rolls without slipping. Well, then you can figure out how that happens by calculating the torque about the axis, right? What's the torque that's produced by the gravity acting on little mass? So like think about this. First of all, if that little mass wasn't there and it was just like a uniform like wheel of cheese or whatever we're thinking this is, would anything happen? No, nothing at all would happen, right? If the wheel is homogeneous, the gravity on the one side and the gravity on the other side, they're both trying to make it go this way and the other one's trying to make it go that way, but they're equal in the opposite and they cancel out, right? So the net torque of gravity on such a homogeneous wheel would be 0. It would just sit there, like, right? Like this yo-yo, right? If I just put it here, it just, it will sit there, right? This isn't level apparently. So, but on the other hand, if I put this little mass right there, all of a sudden, right, there's a torque, right? Because gravity is pulling down on that little mass, and that's trying to make the wheel roll this way, right? It's trying to make it roll like that. So I've got mg, and I can draw this picture. All right, so like what's the part that's torque? It's the part that's perpendicular to the radial arm, like this piece right here. So if this is my theta, and the picture looks like this, it ends up being mgr cosine theta. That's my torque. All right. Now, what is this equation here? This is the Newton, the rotational analog of Newton's second law, namely I times alpha. So alpha is the angular acceleration, namely d squared d theta squared dt squared. My moment of inertia here, I've got this 1/2 mr squared. We keep doing that's our favorite formula, right? 1/2 mr squared, the moment of inertia for a disk. And then, how about this little m? See, why is this r squared? Well, in my example we just did over there, we put the cat at radius a from the rotation axis, right? This one, we're at radius r from the rotation axis. So that's why I have a little m here. Little mr squared is the moment of inertia for the little mass. All right, so lo and behold, this is the differential equation that we have to solve to find the equation of motion. So how many of you are in differential equations right now? Nobody? Not going to happen? All right, fine. Every so often somebody takes this course later and they've already taken differential equations, just not right now. That's cool. Well, the good news is you're not missing anything, because we don't learn how to solve this differential equation in differential equations, because this is a nonlinear differential equation. Like, we cannot solve this directly. It's too hard. However, if we look at a particular approximation, if we were to look at the case that we're down where theta is like, so the mass is like either like up here or down there, like either at the top or the bottom, we can approximate cosine theta. So what I do here, I put theta equals to pi over 2. At pi over 2, the torque is 0, right? So that's one thing. And the torque, I say the torque is mgr when theta equals to 0. That's kind of expected, all right? Now I say, suppose that we've got beta, which is theta minus pi over 2, which, trying to think of how to picture that. I think that, excuse me, that would make beta measured off the, like down here. Anyway, so if we do the math, we get beta double dot is theta double dot, and cosine of this shifted by pi over 2, beta, it gives me minus sine beta. And so what this all means is if we shift the angle like that, we find our way to the differential equation minus d squared beta dt squared equals to minus omega squared beta, where we're using the small angle approximation for sine. So if we replace sine beta with beta, all of a sudden we've got a differential equation that we can solve. I've talked to you guys about solving this before. We looked at this to write down the equations of motion for the spring, right? This is the same differential equation that we had to solve for simple harmonic motion. In other words, in a certain angle, this mass on a coffee can or something is just like a spring on a mass. It's this simple back and forth rocking motion with respect to angle. It's a simple harmonic oscillation in terms of the angle. Approximately speaking, of course. But you can actually do more, because this omega squared actually involves the little mass and the big mass of like the wheel of cheese that we're attaching the little mass to, let's say. And that's the angular frequency. And we can calculate the period of that rocking motion would be like this. So you could actually try this out, right? You could take a giant wheel and put a little mass and just give it a little nudge and let it wobble back and forth. And if you could measure the period carefully, it should follow this rule. That should be something like the period of a rocking motion for a system like this. All right. So this is kind of like generically something we can do for tons of different systems, is we can make an approximation close to a point where you have some kind of like stable equilibrium. Because if you think about it, right, I wish I had some kind of giant wheel of cheese here. I just don't have any with me. Sorry. But if I had a giant wheel of cheese, right, and I've got a little, or maybe a giant wheel of styrofoam would be better, right? And then you've got like a little lead ball towards the bottom, really close to the bottom, and you just give it a little nudge. It's just kind of like rock back and forth, right? Like it's a stable equilibrium. You're just rocking back and forth as the wheel rotates, right? So it's like a stable equilibrium. Anytime you have some kind of stable equilibrium, essentially the mathematics that we're looking at here is behind the scenes, and it can be in some way or another reduced to a simple harmonic oscillator. So simple harmonic oscillators are really important to physics. They're everywhere if you go looking for them. Oh, here's another one. Suppose you have a wrench that's infinitely long. Then in principle you can create infinite torque. Check this out. If Mr. Top Hat applies 100 newtons as pictured, then the torque, R times 100 newtons, goes to infinity as R goes to infinity. Behold, my excellent picture. So, as you can see, this is Mr. Top Hat. As you can clearly see, there's a top hat, or perhaps a conductor's hat. I'm not sure really. It does look a little like a train conductor there, but we used to always joke that the engineers were going to be train drivers. That was the greatest joke I had when we were undergraduates, and we wanted to make fun of the engineers. We say, a bunch of train drivers. Are you offended? No? Train drivers make good money? That's the kind of answer I would expect from an engineering student. Very good. All right. So, anyway, if we had a very long and comically oversized wrench, and we had a ridiculously large bolt like that, and we could in fact put 100 newtons like that, then as long as the wrench is R times 100 newtons applied perpendicularly, that's the torque, right? So it seems like you can get infinite torque from just having an infinitely long wrench. Is this true? I mean, there's physical. What's that? If your wrench, yeah, so first of all, your wrench has to be tough enough to like not collapse under its own weight, right? But we do use this principle, for example, to like break loose, like lug nuts on like 18-wheelers or something, right? You'll see these breaker bars they have that are like, as tall as a dude, like 6 feet long, and you just, you can put a lot of torque if you can apply it so far away. So it doesn't seem like it's kind of a something for nothing kind of thing, right? What are the units for torque? Torque is what? R cross F, right? Which is what? I mean, RF is a force times the distance, right? That's a what? A Newton meter, which is also known as a joule, right? The units for torque are joules. Torque is a energy. And so doesn't that say that you can just create more and more energy if you just have a longer and longer wrench? Like what's the rub? Why isn't that quite the right idea? What's the deal? In order to, if you think about it, you have to have 100 newtons here, right? But you have to apply it over a longer distance to create the same change in angular momentum, right? So I have a picture down here that's kind of instructive. If we have, if we want our output force to be 100 times our input force, then, we need something like this. You could figure out what it needs to be, L and R. I work it out down here, right? If you want to multiply your force by 100, we need, if it's just barely balanced, right, like a teeter-totter, so we have this torque and that torque are balanced, that torque being 0, so that it's just the change in angular momentum is 0. It's not rotating. These are just balanced torques. So F out times L minus F in times R equals to 0, which means that the ratio of F out over in times L should be 100L, which tells me that I need 101 times this length in order to achieve this force multiplication. How can we just multiply the force? Like what's the rub? Well, I'm applying this force 100 times larger here, right? But in order to make the application of this force go 1 inch, how many inches do I have to apply the force over here? like 100 inches, right? So you have 100, or maybe 101. I forget. Maybe, I don't know. I have to be careful with the details here, but either 100, 101, I had to think about it. But, you know, I have to apply the force over a much longer distance here to produce a very short distance but larger applied force over here. In fact, the energy in is equal to the energy out. So basically force times distance is equal to force times distance. So little force times longer distance is equal to much greater force times proportionately smaller distance. But energy is still conserved. It's not a way of creating something from nothing. It's just a way of being able to, you know, but this is still useful, right? Because we can apply a much smaller force over a greater distance as opposed to creating a very large force. We just can't do that, right? I mean, unless we're like, you know, Batman. Actually, Batman's just got toys. He really doesn't do anything. Uh-oh, what's this? Oh, I think I just double scrolled into gravity. I guess that's it for today, guys. So have a good weekend. If you got questions and you're in CFA, feel free to talk to me.